So without further ado, I think we're going to hear from Dr. Statland. And this introduces really the scientific and new approaches that are coming down the pike part of today's program, where we're going to hear 3 talks on the clinical research, but also some of the basic science and translational research that's going into new efforts in FSH. All right. So
I need some help here.
Mic up there. Got it. Hopefully find you in here someplace.
I think it's under Statland.
Should be.
On the screen. Whoops.
There it is.
Yeah. And just take the play thing. Yep. Awesome.
You ready?
Yeah.
Good. Okay, here's your
All right. What do you want?
battery pack in case you're walking.
Excellent. And all right. And thank you so much. I want to thank the organizers for inviting me to come here and speak to you today. Can you all hear me? Okay, great. And what I want to talk to you today about is getting ready for clinical trials. And now, typically when I do this, I'll talk about programs that we have, looking towards the future, various initiatives that are just getting started. But I thought today I would do just the opposite. I'm going to look back in time. I'm going to look back at a natural history study that was done in the late 90s, and the primary outcome they had from the study, which was a measure of strength. And I'm going to look at it thinking about what can we learn that was done right in that study, and where are the gaps that we really still need to fill in to be ready for clinical trials. So who am I? I'm an associate professor of neurology. I work at the University of Kansas Medical Center. I spend about 70% of my time doing clinical research. You can see here this really nice picture with a tree and a beautiful brick building. If you come to Kansas City to participate in any of our studies, that's where you'll go. Where I work is actually not there. You can see I'm only going to show you an aerial photograph of it. It's next door, but it's kind of a dungy brown building. But if you come, you'll get to be at this very nice building. I did a fellowship in experimental therapeutics, which means I studied the design and conduct of clinical trials in people. I'm the director of our MDA clinic, and I've been doing work in FSHD since 2010 with my mentor, Robbie Tawil, who some of you may have met, who works at the University of Rochester Medical Center. Together, we have a large study we're doing now, getting ready for clinical trials in FSHD we call Resolve, which is occurring at 8 centers in the US and 3 in Europe. And we've also put together an FSHD clinical trial research network, which I'll talk about a little bit during this talk. And I know we've done this a few times, but like I have to say, a lot of people deserve applause for getting this set up. And we've thanked John Day and we've thanked the FSH Society, so you can give yourselves a round of applause now. So FSHD is at an inflection point. The elucidation of the unified model for FSHD in 2010 identified a target for therapy, this protein DUX4, which when it's there is toxic to cells. And I think you're going to hear a lot more about that in the following talks. But this really shifted the kinds of questions that we're asking, from what causes FSHD to how can we treat it. It's the accumulation of decades of research. And it doesn't mean that there aren't any more unanswered questions, because there really are, about the pathophysiology and the genetics, but rather it's a sign for us to start building the tools that we're going to need to hasten drug development. And it's going to really require us coming together as a community, because it's the people who have FSHD, the caregivers, their advocates, researchers, and industry all have to get together to develop meaningful therapies. This is the clinical trial landscape as it exists today, and I think it's really a hopeful time. I remember I gave a talk like this 3 years ago, and what I told people was, I think in the next 3 years, we may see some therapies for FSHD that aren't really disease-specific, and in 3 to 5 years, we may see our first disease-targeted therapies coming out. And if we look today, indeed, that's been true. Acceleron has a study of a drug that's designed to increase muscle growth. It works on the myostatin pathway, so a pathway not specific for FSHD that may help it, where they're directly injecting it into people's ankles or muscles in their leg and their biceps. And this study's completely enrolled, and we should get a readout on it late in the summer or early in fall. There's currently a study still recruiting of recombinant growth hormone and testosterone, again, not disease-specific, but designed to increase muscle mass or function. This is going on at the University of Rochester, and you can contact them if you want to participate. And just recently, Fulcrum Therapeutics announced the first disease-targeted therapy, and this is set to start sometime later this year. They're repurposing a drug that was originally used in the area of cancer, but it targets DUX4 directly. And so I think that's a very exciting time. So I've talked about clinical trials happening now, so why do we really need to be talking about clinical trial preparedness? Well, the pace of therapeutic development has outstripped our efforts to prepare for clinical trials. And there's several gaps that we as a community really need to be addressing. We need to be getting our sites ready to run clinical trials. This is the infrastructure side, training people, getting our evaluators so they're all doing things the same way. We need to build the tools that we're going to use to measure response to therapy in the setting of a clinical trial. And we need to understand the personal experience of living with FSHD, because we're not really trying to prepare just for those few studies happening now. We really want to be prepared for all those future studies that are going to be coming up, and we want to be sure that if a drug's approved, that it's actually working, or if we say a drug doesn't work, it really has no benefit. So this is what I told you I was going to do. You're going to see this graph a lot in this talk. And it's a measure of strength. It's the take-home figure from the prior natural history study done in the late 90s. These were individuals who were clinically affected, had a pattern of weakness to suggest that they had FSHD, but this was before genetic testing was routinely done. Each of these little plus signs is a separate individual, and so you can see that these people gave years of their lives to help get us this graph that we're looking at. And researchers like me spent many years to make this happen, over 6 years to get this study up and running and then to do all those assessments. And I want to use it as a launch board to go over several concepts in trial design and outcome measure development. And so I'm going to have to do just a little bit of defining, hopefully not too much. But outcome measures are the tools we use to tell if something in FSHD has changed between 2 points in time. It can be something that we measure in the muscle or in blood, in which case we call them biomarkers, or something an evaluator assesses, in which case we call it a clinical outcome assessment. This can be things like strength or your ability to climb stairs or get out of a chair. Or it can be something that you report directly, like filling out a questionnaire to describe your own experience of FSHD. I'm often asked, which is the right outcome? Which is the best one that we're going to need for FSHD? And the truth is, there is no one outcome measure to rule them all. The choice is going to depend on the drug, what the drug is supposed to do, and where it's at in its development process. So what we really need is a clinical trial outcome assessment toolbox, and that's what we've been working to try to put together. These are some of the concepts we think about when we're thinking about these tools. The first one, validity, is a concept. It's not a mathematical principle. It's asking whether a test measures what it's supposed to, and does it capture something important for FSHD. Reliability is a little more intuitive. It's saying what you measure one day, you're going to measure the same thing the next, given nothing's changed in FSHD. Its correlate is this idea of responsiveness, which says what you measure one day is going to be different when you measure it the next, assuming something's really changed. Risk factors are what they sound like, something about you that we could know today that would predict something bad or good happening in the future. This idea of clinically meaningful change is a little bit complicated, but a lot of these tools produce numbers. So we're often talking about a change of X% or Y, and this is the question of how do we know what percent change in this tool or this measurement is going to be important to someone who has FSHD. And last, but also equally important, is cost and feasibility, because if it's too expensive or you can't teach the technique, you can't do it at multiple sites, we're not likely going to be able to use it in a clinical trial. Which gets us back to this figure, and the first thing you may notice about this figure, I say I'm measuring strength, but I'm measuring something called MMT, and this y-axis is the change in MMT. So what is MMT, and why would it be a good way to measure FSHD? Is it appropriate? It has its origins in the standard scale we use to measure strength in the clinic. The Medical Research Council published this scale in 1943, originally for the investigation of peripheral nerve injuries, but it makes sense in FSHD and muscle disease because it's measuring power. It's measuring something we called isometric strength, which just means your power against fixed resistance. And this is the way we do it. An evaluator puts you in a standard position and then has you contract against their arms. And so we have ways to teach people how to do this. And if you look at the scale itself, well, it's lasted over 70 years because there's something fundamental about the breakdown that makes sense. 5 would mean you have normal strength and you would have a full range of motion. 4, you can still, say, reach your arm over your head, but now you're weak, and so you'd have trouble lifting something or doing something above the height of your head. 3, you would still be able to lift your arm, but you really wouldn't be able to do much with it once you have it up above you. 2 would mean that you couldn't really lift your arm standing up, but if you lie down and take gravity away, you may still be able to pull your arm above your head. 1, there's some movement in a muscle, but it's not functional, and 0, there's no movement. So these are hard breakpoints that make sense. And what's nice about MMT is we can pick the muscles because we can do this across almost any muscle group that match the condition FSHD, and that's what they did in the natural history study. You can see that they picked muscles from the arm, the shoulder girdle, the thigh, the ankle. On this graph, what you see, those bars represent 50% of the people. The little dotted lines are the rest of the individuals. And you can see at the top is normal strength. And for every one of these muscles, people had this full range from being strong to being less than anti-gravity strength. And so they were all involved in FSHD. So one thing you could do is you can average across all of them, and this gives you a snapshot of where someone would be at any given point in time. And that's what they did for that study. The other thing we might be asking is, well, what else do we know about this way of measuring things? We want to get drugs approved for treatments. Has the FDA ever approved a drug based on this type of a measurement? Indeed, manual muscle testing was used just recently for the approval of Emflaza, which is for Duchenne muscular dystrophy, which is another type of muscular dystrophy. And so, yes, there's regulatory experience with it. Does it address something that's important to people who have FSHD? What I'm showing you in this table are the results of a survey that went out to several hundred people. This was run by Acceleron at the start of their study in association with the FSH Society, and they asked people to rank symptom categories by whether or not they had them, and if they did, how impactful it was on their lives. And if you look on the top left in this dark green boxes, these are the most prevalent and impactful symptom categories, and the top 3 all have to do with weakness. So measuring strength in FSHD would seem like it would be an important thing to do. It's easy to perform, it's inexpensive. We can actually test many muscles fairly quickly, about 30 in a half hour, and it's already been used, as I mentioned, in some clinical trials. Which brings us back to our table. Now we know MMT measures an aspect that we think might be important. Each of these crosses is a summation score, a snapshot of someone and all their muscles in their shoulder, leg, and arms. The y-axis will be the change in their total strength from baseline. positive, getting stronger, negative, getting weaker. The x-axis is follow-up time in months. But before we can really start to analyze a graph like this, we have to know, well, how confident are we that if there's a change, it's a real change, not just noise in the measurement? This is a concept that we call reliability. What you measure one day, you can measure the same thing the next, assuming that strength hasn't actually changed. It reflects a number of features: the inherent variability in the technique you're using, what happens in FSHD from one day to the next. Some days you feel stronger, some days you feel a little weaker. And the training that we give to our evaluators. For the natural history study, they trained all their evaluators in the same way. They got together to make sure the technique was right. They were able to show that the same person making measurements on different days, they got the same values, and that two different people making measurements on the same individual got similar values on the same day. Indeed, they then went on, and the same evaluators participated in one of our early clinical trials of albuterol. One of the time points in that trial was 3 months, which would be a time frame of which we wouldn't really expect there to be a large change in strength. And what you see on this graph on the x-axis is that strength snapshot at baseline, and on the y-axis is the same thing at 3 months. There's a line down the center. So if the values are identical, they're going to fall on that line, and you can see that by and large they do. So the reliability at 3 months is quite high for this technique. The spread around that line is telling us something. It tells us about the natural variability in strength in FSHD, but it also tells us about how well we've trained our evaluators and how well the technique's working. How do we do this now? Well, in order to ensure this common training now, we put together a research network specific for FSHD. We have 8 sites in the US and 3 in Europe participating, and each year we fly all their evaluators in to the same place, and we do training. They get together and talk about the different techniques. We bring in people who have FSHD to make sure that they're training on a person who actually experiences the weakness, and we ensure that we can get this reliability. And we're also now working on virtual methods for training, either using teleconferences and videos to help train our evaluators in between these yearly meetings. Which brings us back to this graph that we keep returning to. Now we understand that each of these crosses is a summary, a snapshot of the whole body, and we feel pretty good about the reliability, that if we see a change on the scale now, we can believe that an actual change has occurred. The first thing I notice when I look at this graph, though, is that at any specific time point, there's a very wide variability in strength. And so this may make you wonder what determines why someone is stronger or weaker at any given point in time. Some of you may already be a step ahead of me and go, well, I think I know. It might be how long I've had symptoms. I've had symptoms for 20 years. Maybe I would be weaker. And well, we can look at that. We can look at the time since diagnosis, which you see in years here on the x-axis, and that summary strength score on the y-axis. And indeed, you can see the longer someone has FSHD, the weaker they're getting. But you can notice that there's a tremendous amount of variability around that. So the amount of time that you've had symptoms explains some of it, but it really doesn't explain very much. And now some of you may be going, well, I know what the next point is, because maybe it's related to the genetics. I know I had that gene test. Maybe there's something there that can tell us something about whether we'll be weak or not. Indeed, some of you may know that what we end up with is a number of repeats, in that we get in FSHD somewhere between 1 and 10, and that the smaller number of repeats has been associated with a more severe disease. I believe you may hear more about this later. This is a similar graph to the duration, with the repeats on the x-axis and the strength on the y-axis, and you can see indeed there is an association there with the smaller number of repeats being weaker, but again, a very wide variability around that. And so we can mathematically think of putting these two things together, the mutation and the duration, and say, well, how much of the variability can we explain with those two features? Well, even with both of those, we're really only explaining about 35% of the variability in strength that we're seeing, which tells us that we actually know very little about why someone is strong or weak at any particular point in time, and we know even less about what's going to predict what happens in the future. Well, you may go, that's a little discouraging, but I would say still a graph like this does teach us a number of very important points. The first thing we can look at and we can evaluate is if we take a group of people with the entry criteria here, which was just weakness in a pattern consistent with FSHD, what happens to them over time? And over time, we see a slow but consistent drop in strength of about 3% per year. You can turn this into a mathematical formula. That's the change divided by the variability. That's what we call responsiveness. In this case, you can see it's only modestly responsive because the variability is much larger than that change. It can also help me in the clinic, inform people about what to expect over time, because I can say, well, over time, you might expect to see a slow but steady loss of strength, but at any given moment, that may be different. You could get a little stronger, you could get a little weaker. But it does allow us to make a number of important things for clinical trial preparedness, because it allows us to plan for clinical trials. If we had a drug that was going to halt progression, we could figure out how many people we would need to enroll in that study, and that would be 320, which is a large number of people for a rare condition like FSHD. But let's say that drug was going to halt progression, and then you are going to get stronger. Well, suddenly, the number of people that we need, 80, is quite reasonable. And we could achieve that in FSHD, which leads to this next question, which is, can you get stronger? I'm often asked this in clinic because people are asking me, can I get stronger if I do something like exercise, or if I start an intervention, is there any chance that I can improve in strength? And this natural history study tells us something about that, because all these people above that dotted line at 0 are getting stronger, and you can see that people are getting stronger even up to 2 years into follow-up. And indeed, we've done a study since then. This was a study of exercise plus a drug called albuterol, and what you can see is that blue line is the natural history data I showed you here, about a 3% loss per year. The green colored graphs are people who did some exercise, and so you can see they improved in strength, and this persisted to some degree out to a year for many of these individuals. So what we know, MMT measures a seminal feature of FSHD. It correlates to other clinical features like duration and mutation. It can map the patterns of weakness in an individual as well as progression. It's reliable, fast, inexpensive, and can be taught to our evaluators who do these measurements. It shows us FSHD is quite variable, but in large populations is slowly progressive and can be used to power studies and inform our sample size calculations. But there's room for improvement. Some of you may have already noticed that at this last time point, we only had a third of the people at the beginning. And so a number of people dropped out. What if those people were the people who were stronger? Well, that might bias our interpretation of what happened over time. We did not evaluate the relationship between the mutation and progression because they didn't have that information when they did that study. We didn't have enough individuals in the study to answer important questions about risk factors for progression, and we don't really know what a small change like 3% in this MMT score means and whether it's meaningful to someone. We can apply the lessons that I've been over here to everything that we're doing. The same questions we have about MMT still need to be answered for all our major functional outcome measures we use in FSHD. The same questions will need to be answered for our biomarkers as well. We need early signals a drug reaches its target and has an effect, because studies using strength may require a long time, 1 to 2 years. We need to know what a meaningful change would be for our outcomes. For example, if we had a drug that only changed a biomarker but not strength, would you be willing to keep taking that drug for many years, which is likely what you might have to do, or maybe even for the rest of your life? And we need to demonstrate the ability to train our evaluators and our coordinators so they're ready for these trials. Which brings me back to the network and the studies we have going on now. We have a major study going on in the network to assess strength, function, and muscle quality. 220 people will be following for 18 months. We're about halfway through recruitment, so we're still looking for volunteers. Each of the things we've talked about today, well, that's what we're trying to determine: the validity, reliability, responsiveness, minimal clinically important change. We're trying to identify those risk factors for more consistent progression. We have 2 studies going on to assess MRI and muscle biomarkers for these disease-targeted therapies, and we're hoping that this infrastructure can not just be used for studies, but also to help us improve care everywhere. There's many ways to participate. And I just want to conclude showing you a lot of different ways for you to get involved, and you can get involved directly by being in a study, or indirectly. We have focus groups and advocacy groups that help us with our studies. Kylie Higgs is my project manager. She's very nice and responsive if you reach out to her. You can go to clinicaltrials.gov, which I'm showing you here, enter the word FSHD, hit enter, and all the studies will pop up. When you click on them, you'll get information about the study. You can go to our network, the Clinical Research Network online, where we'll also list our studies and ways for you to contact us. You, of course, can go to the FSH Society website, and I encourage you to join if you haven't. They'll send you emails about current studies and ways to get involved. And you can consider joining the National Registry of Patients and Family Members. This registry has been going on for almost 15 years. It's a tremendous resource for those of you who are already participating, because there's 10 years of follow-up data in it, but they send out notices for new studies to people in the registry. All right, thank you very much. Okay.
Great. Yeah, excellent. Thanks, Jeff.
Yeah. Is there another?
That was great. I'll take that. Yeah. So it's a real pleasure for me to bring up Stephen Tapscott, whom I've known for a couple of decades, and it's fun. I haven't seen Stephen for a couple of years, and the world has changed dramatically in a couple of years, from our era of just trying to find genes to the era where we can actually start manipulating them has made us all much more excited. So I'm very eager to hear what Stephen's been up to and how it's going to move us all forward in terms of developing treatments for FSHD. Thanks, Stephen.
Thank you. It's a pleasure for me to be here speaking with you today. I want to thank the FSH Society for setting up this opportunity. I'm clinically trained as a neurologist and trained in research as a biologist and molecular biologist. And I've been working in FSHD research for maybe 15 years or a little bit more than that. The title that the FSH Society asked me to base my talk around is Why We Think FSHD is Treatable. And I'd actually like to change that title to Why We Know FSHD is Treatable. And I hope to convince you as we go through this that we're really at the cusp or at an inflection point, as Dr. Statland said, that we can move on to really rationally develop treatments for FSHD. Maybe not cures initially, but at least treatments initially and then ultimately cures. And so standard genetic approaches in families with FSHD were used to identify where the mutation in the genome was that caused the most common form of FSHD, FSHD1, and it mapped to the very tip, the Q tip of chromosome 4. You have a P end of the chromosome and a Q end of the chromosome. This was the 4Q end of chromosome 4. So they knew where the mutation was, and then they soon identified what the genetic change was that caused FSHD, and that was a surprise. So in that region, in the very tip of chromosome 4, there were these what were called macrosatellite repeats, 3,300 nucleotide sequences of DNA repeated again and again and again, tens to hundreds of times in that region. And individuals with FSHD had lost a subset of those repeats, so they had 10 or fewer repeats on that 4Q chromosome tip. And if you then blow that up, here's the chromosome tip, these repeats, and if you look at just one of the repeats, again 3,300 nucleotides, and about 1,000 of those nucleotides encoded a transcription factor called DUX4. So what are transcription factors? Transcription factors are genes that are made into proteins, and then those proteins identify sequences in the genome that are in front of subsets of genes, and they turn on those subsets of genes. So they read the genome and they tell the cell what to do, what proteins to make and what to do. And so for many years I studied a gene called MyoD that was turned on in muscle cell and turned on all the genes you needed to have to make the muscle cell. And so they can inform a program of activity for a cell type. And so what happens in FSHD is that normally in skeletal muscle you would have all of these repeats, and the repeats would be silenced so that DUX4 gene could not be made in the skeletal muscle. The most common form of FSHD, FSHD1, you had too few repeats, and that would lead to less complete repression, and you get a leaky expression of this DUX4 transcription factor in the muscle. In addition, we've subsequently learned that FSHD2, almost identical disease clinically, is caused by having a relatively small size repeat but in the normal range, and then mutations in some of the genes that are responsible for silencing that area in skeletal muscle cells. So SMCHD1 mutations are the most common, but other genes are involved in silencing that region as well. But whether it's FSHD1 or FSHD2, the final cause of the disease is this leaky expression of this DUX4 protein in the skeletal muscle. And so what I'm going to do for this talk is sort of walk you through the elements that I'm arguing support therapeutic development in clinical trials at this point. And this is the guideline of what we'll be talking about today. And I'm going to start off that we have clear genetics and clear mechanisms that make us confident that we know how to diagnose FSHD and we know how to determine an approach to identifying patients for clinical trials. And so, as I mentioned, in FSHD1, we can measure the small number of repeats. For FSHD2, we can determine if there are mutations in factors that repress that region of the genome. And individuals can have both FSHD1 and FSHD2 as well, but all of them result in the expression of DUX4. Now, that's the simple story. Things get complicated. I told you that on the 4Q chromosome, you have the D4Z4 array. There are actually several flavors of that 4Q chromosome. I'll just call it the A flavor and the B flavor. If you have a small number of repeats on the A flavor, DUX4 RNA gets made, it makes the protein, you get FSHD. The B flavor, some people have a B chromosome 4 instead of an A chromosome 4, and that has some sequence differences that prevents the RNA from being made in a stable form. And so even if you have too few repeats on this B flavor of the chromosome, you won't get FSHD. And so, but we can determine that, and we can measure, do you have an A chromosome, do you have a B chromosome, do you have a large number of repeats, a small number of repeats. And so this is a image from the University of Iowa website that does the DNA testing. And from this knowledge, you can get just a very rational approach. If you get DNA from an individual, you can run it on this southern blot gel to separate it out and ask, do you have an A allele or a B allele? If you have a short A allele, then you have FSHD. If you have no short A allele, but you have at least one A allele, does that have hypomethylation? And then that might mean you have an SMCHD1 mutation, then you have FSHD2. And so without walking you through all of the branches in this, there is a very rational way of doing it. It's not easy, it takes time, but we can do this. And so from this, we can really think about FSHD as a disease spectrum. If you have a very small number of repeats, you tend to have more severe disease that has an earlier onset, sometimes a pediatric or infantile onset. Repeats in the 3 to 7 region, it's sort of classically inherited dominant disease where if you inherit this, you have a high likelihood of showing signs of FSHD. In the 7 to 10 region, you might have a few, 7 to 10 repeats and may or may not show signs of FSHD. However, if you have repeats in that range and a mutation in SMCHD1 or the FSHD2 genes, then you will show penetrance in this region. And so there's a really rational way of thinking about the different genetics and the different severity of the disease. In general, every individual is a little bit different, but in general we can understand this. And then there are complications. There are some people who never fit into this pattern, and we're learning about them. Some of them have very complex rearrangements and duplications that change the region, and they take more effort to understand. But so far, everything fits, and so that's great. And so from that, we have opportunities for genetic studies. If we wanted to enroll just FSHD1 patients with 10 or fewer repeats or compare them to FSHD2 patients, we can segregate these and identify them in the clinical populations, identify patients with both FSHD1 and FSHD2. And yes, there are outstanding questions about complex rearrangements. Yes, it would be good to have better ways of doing the genotyping that didn't take so much time to do. But nonetheless, we're in a very good position for this. We also have a validated target with limited expression in adults. And so the idea is that if we prevent DUX4 expression in skeletal muscle where it shouldn't normally be expressed, and in the adult tissues we don't know of any other normally expressed area for DUX4, we should be able to prevent DUX4 from damaging skeletal muscle. And so to go back to this diagram, the real key feature here is FSHD is caused by the expression of DUX4. And if we turn off DUX4, we should be able to stop the disease. This is an image showing cultured skeletal muscle where most of the nuclei are not expressing DUX4, but this red stain in the nuclei of this muscle cell shows that this FSHD muscle cell has now lost the repression of DUX4 and it has burst on to cause damage in this skeletal muscle. So FSHD mutations result in DUX4 expression. DUX4 then can be made into an RNA and protein in FSHD muscle. What does DUX4 do? I told you that transcription factors read programs in the DNA. DUX4 is a transcription factor. It's normally expressed in early stem cells of the embryo, where it turns on the first wave of gene expression during embryogenesis. And so after fertilization, the embryo goes through 1 or 2 cleavages to form 4 cells, and then it starts transcribing its genome to make it a totipotent cell that can rise to all of the cells in the embryo, and that's where DUX4 does its work normally. And so when it's misexpressed in skeletal muscle, it's turning on this early developmental program in a post-mitotic skeletal muscle that's supposed to be doing something completely different, and it really causes damage to the muscle when it activates this foreign program in the muscle cell. And so for therapies then, we just need to turn off DUX4 and stop it from doing that damage. And this is a busy slide, and the reason I have it up here is not so you can look at all of the different parts of it, but really just to point out that we've identified many of the regions that are responsible for turning on DUX4, both in development and in skeletal muscle, as shown by these different bubbles here, showing different factors that regulate DUX4 expression. And we've identified many of the things that when you turn DUX4 on, that DUX4 does that could possibly be damaging to the muscle down here. And so if you wanted to develop a drug to prevent DUX4 from being turned on, we have a very target-rich environment. We have lots of things that we can use to, as targets for drug development. And in fact, some of them really we do have drugs for already. So for example, this beta-2 receptor, if you knock that out, you turn off DUX4. And we have, if you stimulate that receptor, you turn off DUX4. And there are drugs that are beta-2 agonists that have actually been in trials for FSHD, the albuterol trials that Dr. Statland mentioned earlier, where there was a mild benefit in the trial, not sufficient to move it on to therapies, but also, I think it is a good example of there are drugs that have been tested in people that have efficacy here, and maybe there's something that we can revisit in this regard to make them a little bit better and try them again. But there's also a large space here to examine for new drugs. And again, we have a complex consequence of DUX4. Here it's a little bit more complicated because DUX4 does all of these things in skeletal muscle, and how do we pick which one to target here that we know that it will have a clinical effect? And that's a little bit of a guessing game right now, but there are multiple ways of looking at it. One of the things DUX4 does is induce proteins that are only expressed early in development, and so the immune system is not aware of them, and when they're re-expressed later on in life, they can create an immune response. And so one rational approach from the area down here is to maybe prevent an immune response to those genes. Would that help in ameliorating the progression of FSHD? But at any rate, we have lots of drug development opportunities, and we can use our knowledge now to screen for drugs that inhibit DUX4 expression, either repurposing existing drugs, screening new chemical libraries to identify new drugs to move into people. We can use some of these proteins to screen for drugs that specifically interact with the beta-2 receptors or other factors upstream of DUX4. And we can look at general effectors, such as I mentioned, for immune modulators. So there are lots of opportunities for developing drugs for FSHD. Once we have candidate drugs, we have preclinical models to test drugs prior to human trials. And so there are problems with the FSHD preclinical models. And when I'm talking about preclinical models, I mean either animals or other tissue culture models where you can use the drugs to ask, are they doing what you want them to do? So one of the problems is that human DUX4 has diverged from non-primate DUX genes. And so you can't just simply test the drugs in mice. And so it makes it a little bit harder to take the traditional drug approach for preclinical testing in that regard. And as I mentioned before, we have an incomplete knowledge of the pathophysiology downstream of DUX4. Which of those things that DUX4 does is going to really be the most important for drug development. Having said that, though, we do have lots of strengths in preclinical models. We do have mouse models where the DUX4 genomic region has been put into the mouse, and then we can look at the expression of that human DUX4 gene in the mouse. We have mouse models that express the DUX4 RNA or DUX4 protein, and so drugs can be put into those mice for pharmacokinetics do they engage their target and do what they're supposed to do in a living animal before going into humans. We have some models for the downstream consequences of DUX4, cell toxicity in mice, zebrafish, and other models. And one of the really critical models as well is just taking muscle biopsies from individuals with FSHD and growing the cells in culture and asking if you put the drug on those cells, does it do what it's supposed to do and engage in its target? And perhaps many of you here in the audience have donated your skeletal muscle biopsies to research for that purpose. And I can't thank you enough for doing that to help in our efforts to cure the disease. So we also have good ways to measure disease progression, and Dr. Statland was talking about measuring strength outcome and the efforts that have been put into that over the last decade. He mentioned MRI, and I'll just show you some images. There are abnormalities of the MRI scan in muscle from FSHD that people are very hopeful at this point might be used to monitor disease progression. And so if you look where this arrow is here, that muscle is in an FSHD individual, but it has a normal MRI appearance. This muscle next to it has a slight blush on this MRI parameter called STIR, and so that would be a STIR positive muscle. It's T1 negative. T1 measures fat, and so it doesn't have any fat, but is stir positive, and that means it has edema or free water, sometimes reflecting inflammation. And then this muscle is T1 positive, meaning that it has a fatty infiltration, but it's now stir negative. And from studying a number of different individuals, the model has come up that in FSHD individuals, the muscle starts off with normal MRI characteristics, develops stir or T1, positivity indicating free water or inflammation, and then ultimately fatty infiltration. And so this, in addition to following strengths, is a way to follow progression of the disease muscle by muscle. And if you can imagine, every individual has hundreds of muscles in their body, and each one of them then is a muscle that can be followed for progression of FSHD. And so from that MRI, what do we want to know? We want to know what are the molecular correlates of the MRI signal. So I talked to you about stir and T1. What does that mean really about disease progression, both molecularly and due to strength? Does it correlate with inflammation or other pathology? Does it correlate with DUX4 expression? And the real question right now is, can MRI provide a measure of disease activity or progression that can speed up or enhance trials of drugs in the future? And so these three institutions were involved in a Wellstone study where we enrolled individuals with FSHD, performed MRIs, did muscle biopsies, and measured both strength and the molecular attributes and pathology of those muscles. And we determined that the MRI normal muscles had near normal pathology when you looked at it, had very low expression of DUX4, whereas the ones that were either stir positive or early T1 positive had more active pathology and some inflammation and higher expression of DUX4 in its regulated genes. And then nearly all of the muscles, whether stir positive or normal, had increased fibrosis and signs of chronic inflammation. And so from this, we can get sort of a model of how the MRI both correlates with disease progression and what it tells us about the disease progression. And so again, the MRI normal muscles have mild underlying pathology and very low or no detectable DUX4 expression, but they do have signs of chronic inflammation. The T2 muscles, which is sort of the next progression, have increased DUX4 expression and increased pathology or inflammation. And this suggests a model where initially you might have very low, maybe even undetectable levels of DUX4 that's creating a chronic inflammatory state, and then progression that's associated with higher areas of DUX4 expression and then MRI abnormalities. This needs to be validated and tested, but then that's a model for progression that can be folded into clinical studies to help inform response to drugs. There are outstanding questions, and so this is a hopeful situation at this point. We still need to determine whether MRI or DUX4, the MRI characteristics or DUX4 expression can be used to assess response to therapeutic interventions. Can the gene signatures that we see that correlate with the MRI normal muscle be used to measure disease activity? I said that there are gene signatures there of chronic inflammation. Is that something that we can use to determine response to therapy? And then will these really correlate with functional outcomes? Will people whose, say, inflammation markers go back to normal really get better and stronger? Is something we need to determine, but we have the tools to do this. And we have International Clinical Trials Infrastructure Network that Dr. Statland just talked to you about. In a brief history from international meetings in 2013 and 2015, there was a coalescence about a need to develop these international clinical trials networks. They developed the objective and subjective functional outcomes that Dr. Statland mentioned to you about, and largely to his work and to Dr. Twill and others, really gained support for a national clinical trials network that started in 2016 with 7 initial sites and now with 4 expansion sites and 3 European sites doing these natural history and biomarker studies, and currently funded by NIH and FSH Society and multiple other groups. And so this is just a picture similar to what Dr. Statland showed to show the national and international reach of this clinical trials network that's really getting ready to test drugs that come through for FSHD therapies. And so we need drugs, right? But there are drugs now, which is really amazing. Atir did a clinical trial with Resolaris, an immune modulator. It did not meet its end goals, and I believe they're not pursuing that, but I'm not sure. Dr. Statland mentioned the Acceleron trial using a myostatin inhibitor delivered locally to skeletal muscle. He mentioned the Fulcrum study of a P38 inhibitor. This is a drug that was initially developed by GSK for another indication. Fulcrum Therapeutics identified P38 as a potential modulator of DUX4 expression and then went to GSK and got a drug that's already been through phase 3 clinical trials in humans and now can go very quickly into trials in FSHD. And there are many that are on the way, and this clinical trials network that Dr. Statland mentioned is really a critical infrastructure for pushing these drugs through clinical trials to determine whether any of them will be useful for human therapeutics. And I think the last thing we need is an organized and effective FSHD community and advocacy groups. And certainly we have the FSH Society that set this up today and has been really a key leader in providing coherence in the FSH community in addressing clinical trials in FSHD. The progress has led to really substantial NIH support. Your taxpayer money, your neighbor's taxpayers' money are really going into trying to find the answer for this disease. And then thanks to you, the FSH community, who without your participation and support, we would not be anywhere near where we are today. So thank you very much.
Great, and again, we'll have time for questions afterward, before our break. So I guess I'm supposed to use the mic too. If you want to put that up. So one of the reasons I was excited to move back to California was because of the lab of Tom Rando, whom I've worked with for many years, and he's doing some very exciting things with regard to basic mechanisms that include FSH, and Antoine is going to give us an update on things that he's involved with in the Rando lab. So thank you so much for being here.
Thank you. Thank you, Dr. Day, for the introduction. Does this work out? Maybe I should hold it like this. And thank you to the FSH Society, mainly June, for inviting me. And thank you all for coming. My name is Antoine, and during the week I don a lab coat and lab gloves, and I do the nitty-gritty experimental work trying to understand how muscle works and how we could get to FSHD therapeutics. And today I'd like to give you an overview of some of the experimental work we're doing, broader picture of how do we study muscle, how do we get to an understanding of molecularly and cellularly what's happening, and then how do we deploy that information to actually get to what matters, the therapies for the diseases. And in the background here, you see an example of that which I find personally extremely interesting about the work that I do. What you see here, the circular shape, with the dots, that's a muscle stem cell. And this is a cell that has the capacity to remake muscle, and all of your muscles have them. And in the background, you see a full-grown muscle fiber. Basically, what I am really interested in is how can that small circular shape, that stem cell, it's one of the smallest cells in the human body, how can it make that a large muscle fiber that is in the background? And these are some of the largest fibers. They span tendon to tendon. How do they do it? And if we understand how they can we leverage that information to develop therapeutics, to develop therapies and treatments for muscle diseases? In the talk of today, I'm going to give you a brief outline of what makes a muscle. What are the types of cells that are in it? How do we look at that? And then we go into DUX4 toxicity. It's already been alluded to by Dr. Tapscott before me that it's a protein. The cells have it, they're not happy. So we really want to find out ways that we can prevent the cells from having that toxic protein? How do they deal with it? Can we help them deal with it? And I'm going to focus on particular parts of the research we've been doing here at Stanford towards preventing DUX4 stability. And then I'll end with some future directions of where this research is taking us. So what makes a muscle? Well, the muscles connect the joints. They span tendon to tendon. If you see here on the upper left, you're all aware of that part. They connect large parts of the body and allow movement. If you contract a muscle, you can bring two body parts, two bone parts closer together, and you can move around. But if we take a closer look up, say we make a cross-section of that muscle, what you'll see inside is a bunch of bundles. And if you take a closer look in that, in one particular of these individual bundles of muscle fibers, you'll see that each of those individual fibers is in essence a cell, one of the larger cells in the body. And if we take a very close-up look, this is the most powerful microscope we have, an electron microscope. What you'll see is a very characteristic of these muscle cells. It's a banded pattern. We call this Z-striping, Z-banding. And what you'll see is these dark patches, that's protein. And what's happening here is on the top part there is a relaxed muscle, and you'll see dark patches intermittent with white patches. And in the bottom the muscle is contracted, and you see all the white is gone. What's in essence happening here is you have a molecular lattice that slides. The molecules slide in between one another. And this allows the muscle to change size and generate force. And this is ultimately how you move about, how you move around. And this is something we can see just under the microscope. So if we take a muscle and we break it apart, you can see the individual cells. They're like hairs, that size. But with a simple light microscope, here you can already appreciate that banded pattern. And in this case, I stained the DNA of these cells in blue. And you see the DNA is all the way squashed to the outside. This is one big molecular machine built to generate force. And it's all made up of protein. This is why if you eat steak, people say you eat protein. Because that's literally all that's in here. Now you can imagine if you have a molecular machine of these tiny components that is spanning joint to joint, it's very easy for something there to go wrong. If something gets disorganized or doesn't work properly or doesn't align in the right way, you might do damage. And this is actually continuously happening. And for that reason, the muscle has a very powerful mechanism to repair injuries. And that can be really dramatic. And I'm going to show you an example of that, where we mimic a snake bite. On the left side, we got our cobra snake. I don't handle the snake itself. I just order the venom. But if we take the venom and we inject that into the muscle of a mouse, and this is a cross-section of the muscle of a mouse before it's injured. And what you see is the circles. These are the individual muscle fibers. You see in purple, those are the DNA parts. They're squashed to the outside. It's very tightly compact. But the moment after a snake bites, in this case it's me with a needle injecting snake venom. It's not really a snake. You see that this looks really, really bad. That whole architecture is gone. It's just completely disassembled. You see DNA is everywhere, not much left of the cells. You can imagine a cobra snake. It's dangerous for that very reason. But just a few days later, look again, and you'll see that the pattern has changed completely. It's the muscle has almost completely rebuilt itself. And it can do this again and again and again. And what I really want to know is, how does it do this? And knowing that all your muscles can do it, how come that when you have a certain mutation, this powerful mechanism is no longer good enough? Can we help it? Can we aid it in some way? Now the driver of this process, I already told you at the beginning, this is a muscle stem cell. This is a close-up again of a muscle fiber. You see in the background in green a large muscle cell. And then on top, these round shapes, they're the muscle stem cells, tiny guys. Now from this graph you might say, well, there's quite a lot of them. Well, there really isn't. In fact, I was getting so tired of looking for the right cell that had that image that in the end we just purified a bunch of them and tried to seed them on top so that we could get that. So this is artificial. But the principle is still there. There is this tiny round cell lying on that fiber, and it's there, it's doing nothing, but it's ready in case of severe damage to wake up, and it can remake all of that muscle. And I want to know how it does it. Now that stem cell is different from some of the stem cells you may have heard out in the news. These are adult stem cells, and every tissue has them. And they are geared towards making one tissue and one tissue only. If you go out in the sun too long and you get a sunburn, and you know your sun starts the skin starts peeling off and you get new fresh skin after that, it's your skin stem cells that start making new skin to replace the damaged, the burned skin. And each of your tissues has that. And in the muscle, it's these guys that can remake the muscle after a snake bite. Now the nice thing is we can purify them. And if we purify them, we can put them in a dish and just look under a microscope what's happening. How do they make muscle inside a dish? And what we see at the beginning, all the way on the left, we have that tiny cell. The first thing it needs to do is it needs to grow in size, so we can see that. And once it's big enough, it will start dividing and dividing and dividing. You get more and more. And these cells start to line up. And ultimately, they start to fuse. And once they're starting fusing, they start building that molecular machine that allows them to contract. And contract they do. If we put them under a microscope and we look at them in a dish, you can see these contracting myofibers. It's really exciting to see. Now, while we're doing this, we can, of course, ask, well, what exactly is happening? Which are the genes that are being turned on in this process? When are they turned off? What's happening? And what do we see happening in the case of cells that we isolate from FSHD biopsies? We find that there is this toxic protein coming on, DUX4. And we're not exactly sure when it's turned on. It's probably not all the way in that small cell at the beginning, but definitely here at the end. And you can right away appreciate why the repair mechanism doesn't work properly. Because if a toxic protein is already made in the repair cascade, obviously the cells that are repairing are not going to be as effective. So the real question is, what can we do about DUX4 to get that repair mechanism back into gear? Now you've heard beforehand from the previous speakers that we know a little bit about DUX4 by now. So on the left side we got DNA. DNA is the blueprint of the cell. It encodes all the genes, it encodes all the information that the cell needs to work to become a cell. And the DNA is transformed into RNA, it's read into RNA, and RNA is made into protein. And protein, that's really the machinery of the cell. The proteins are the ones that make up the contractile apparatus in the muscle fiber, but the proteins are also like DUX4. You can bind DNA, turn on other genes. And what do we know in healthy cases, in a healthy cell? There is DUX4 DNA. It can be read into DUX4 RNA, but the RNA is unstable. And Dr. Tapscott mentioned this beforehand. These are chromosomes of the B flavor. They're making the RNA, but the RNA is just falling apart, and you'll never see protein. However, in the case of FSHD, there is a simple change in the genome. There's a single letter change. And as a result, it creates a stability signal. We call this a PAS, polyadenylation signal, complicated word. Basically, it's a stability signal that allows the cell to recognize, hey, this is an RNA we need and it must be stable. And what does it do? It'll tag on a poly-A tail. Basically, a series of letters are all A's. And the moment that tail is on there, the RNA is stable, and what will happen? DUX4 protein is made, and the protein is toxic to the cell. Kind of a catch-22. The cell is recognizing something it shouldn't recognize, it starts making more of it, and it will kill the cell. So here's the thought. There's multiple ways we can intervene with DUX4 function, right? We can prevent the toxic effects. We can go all the way upstream and go to the DNA and make sure that the cell doesn't recognize there is a gene there in the first place. But I was thinking, what about the stability signal? What if we prevent the cell from recognizing that as a stability signal? If we do that, we're basically on the left side of this slide. It will make DUX4 RNA, but it's not stable. It will just fall apart, and you'll never have the toxic effects. Now, and this is an idea, in a way it's crazy, but because we know how long that sequence is, it's only 6 letters in the DNA. And we have billions of letters in the DNA, so statistically we can calculate that there's 10 in the average gene. However, we know that every gene only uses 1. So if every gene only uses 1, it's ignoring 9 others that are perfectly valid. How does it do that? How does a cell ignore 9 of them and pick one specific one? If we understand how the cell ignores those other 9, hey, can we use that information to make it specifically ignore that signal in DUX4? Now this is a long shot, and this is something I would like to stress why societies like the FSH Society are really important. We know nothing about this because we don't have an idea of stability signals, how they work. We don't really know how this mechanism of ignoring those signals works. It should be there, but what does it look like? What's happening? And if you knock on the door of the NIH and ask for money to investigate that, they're going to say like, yeah, well, that's a risky business because you don't have the tools, you don't know what you're looking at. And it's actually smaller organizations like this that could give the small amount of funding to kickstart the idea and just ask, is it feasible? And the small grant from the FSH allowed us to start this work, to start looking at what's happening. Now, in order to study stability signals in DUX4, DUX4 is actually not the right one to target. And I list here a couple of ideas, a couple of things we know about DUX4. It's expressed in muscle. We have RNA and protein that we want to measure, and it binds to DNA as a functionality. But the trouble is it's very small. It only has one of these stability signals. And the second thing is it's a toxic protein. So if it's there, the cells are going to end up dying. So it's going to be really hard to actually measure anything around this stability signal, because if it doesn't use it, well, maybe we have indeed measurable RNA. But if it does use it, the cells start dying. So what are you really looking at? So we were looking at a better thing to study. And we found a distant relative, a very similar gene to DUX4, but different in some important ways. It's expressed in muscle. It's a muscle gene. Like DUX4, we can detect RNA and protein. And the protein has a similar function. It binds to DNA. However, unlike DUX4, there's multiple of these stability signals in there. So we can actually use PAX3 to detect which stability signal the cell is using. And more importantly, it's not toxic. So no matter what happens, the cell will survive if we start changing it. So we wanted to study the stability signals in PAX3 in order to understand how does the cell recognize the stability signal in DUX4, and might we intervene with that. Now, of course, this requires setting up new technologies because we need to measure the length of an RNA transcript. So what are we having here? On the top part, this is the DNA, this is PAX3, and you see there's 3 stability signals. There's 2 of them. 2 of these PASs are really close in the front of the gene, and there's one all the way to the end. That gives us 3 different RNA molecules. We call that isoforms, 3 different variants. There's short ones, 2 of them, and then there's a really long one. And they'll generate protein. The interesting part about PAX3 is that the long one does not translate into protein. And that's because there is an inhibitory mechanism in place, and that's actually really nice for us because we can see the outcome on protein, which is what we're ultimately interested in for DUX4. But now in order to study this, we need to measure the difference between this guy and that guy. And that requires us to look at something that is basically 100 nanometers in length. So think about an inch and then 1/1,000,000th of that size. And I need to know whether we're looking at that one or that one. And our microscopes are not able of doing that. So we had to adapt some technologies to actually get to that resolution. And this is something I was able to do a couple of years ago. Finally, we were successful. Where if we look at PAX3, I was able to dye the first part, the front part of it, in green, and the back part that is only present in the longer RNA in red. And now if I stain the cells, all I can do is look at each cell. In this case, the cell is marked by DNA in blue. And I can count the dots. And these are individual molecules. And these dots are green as well as red. So all of these are long. They have used the last stability signal. And in the cell below, we see 5 green dots. Only one of them is also red. So in this cell, most of the cells are using one of the first stability signals. And the real question is, what's happening in this cell? How is it able to ignore those stability signals? Because if we understand that, we have what we're looking for. So what I then did is I counted these dots in cell after cell after cell, looking to find a pattern where cells routinely make one choice or the other. And I found that in the end by isolating stem cells from different muscle groups. And in this case, in this graph, I counted the distribution of the different RNA molecules. There's 100% in total. And I counted that from in cells isolated from limb and from the diaphragm muscles. And what you'll see here in red is the amount of long molecules. You see in the limb, most of the cells make longer isoforms, longer molecules. Whereas in the diaphragm, it's the opposite. This is largely blue. Most of the cells express the shorter isoforms. So the real question then is, what are these limb cells doing? How can they ignore that first stability signal? So I did a lot of comparisons, isolated many cells, and asked, well, what are the genes that are different? What are the biochemical processes that are different? And I'll cut to the chase. It's one gene. It's called U1 snRNA. And it's 3.5 times as high in limb muscle stem cells as it is in the diaphragm. And we know it's specific because if you look to its closest relatives in terms of genes, they're conveniently named U2 and U4. They're not changed at all. So is U1 the factor that allows these muscle cells to ignore their stability signal? And we tested that, and it appears to be the case. So in this case, we knocked it down. We removed the gene from the cells and asked, well, what happens to the length of the molecules of PAX3 that are made? And we see that there is a drop in the longer isoform as a % of total. So yes, the cells are now suddenly starting to choose the first stability signal. Does that affect the amount of protein that is made? Absolutely. You'll remember that the longer versions, they're inhibited. They're not making protein, but the short ones, they are. And we start seeing an increase in protein. Can we do the opposite? Absolutely. We can send in more U1 snRNA into these cells, and what happens? We see the amount of protein go down. We can force the cell to ignore the stability signal. And we can actually see the effect on the amount of protein. So now this leaves us an interesting point, because on the one hand we can start looking at DUX4. We actually have a mechanism. We have something that can modify the stability signal and the cell's ability to recognize it. But at the same time, we're doing basic biology here. We're exploring things about PAX3 that beforehand we didn't have a reason to looking into. So I was wondering, like, what's happening to the cell? Is PAX3 important? And we treated it. We removed it from the cells by modulating U1 snRNA. And what we saw is the muscles are getting smaller. So we measured here the size of the muscle, the mean fiber size, the individual muscle cells, and we thought it was getting smaller. Then the question is, does that mean that PAX3 is important for maintaining muscle strength? And here's a question to you then. How do you measure how strong a mouse is? These are the kind of questions that I routinely face. Like I want to understand how strong it is, but how do you do it? What we ended up doing is a simple experiment where we put the mouse on a grid, and the grid is tied to a force meter. Now, of course, I can't pull the mouse because then I'm measuring how strong I am by pulling on a mouse. So what I have to do now is wait. The mouse is holding on. At a certain point, the mouse will be like, okay, I'm going to try and get away. But I'm still holding it still. So it will pull, and I can measure how strong it is. And what we see is that a normal mouse gives a certain strength measure, but without PAX3 long term, the cells the mice are slightly less able to pull with a certain force. So it seems that they are weaker. I tried a different experiment where I put them on a treadmill. This is very similar to going to the gym, except there is no TV in front of them to keep them going. And they just run, and at a certain point they're tired, and then they'll roll off the treadmill, and then they're fine. And they actually like doing this. They can do it for up to 2.5 kilometers. That's 1.5 miles in one go, which I find amazing. But we'll see in this case, if we take PAX3 away from the muscle, we see indeed that they run less long, consistent with the mice being a little weaker in general. So this is an example of how doing basic biology gives us new insights of how the muscle works. And that could give us surprise discoveries that maybe if we boost PAX3 a little bit, maybe that's an overall idea of improving muscle strength and muscle performance. And that's an idea that beforehand we wouldn't have had. So some of the conclusions to wrap this up, we demonstrated that muscle cells can ignore a specific polyadenylation signal, a specific stability site, and that it's U1 snRNA is the gene that is doing that. Now maybe there's others, but this one is definitely there, and it can censor a specific polyadenylation site. And we know that if we do that, we can actually see changes in protein, which is ultimately what we're after for DUX4. And we had a chance discovery that PAX3 is actually important for muscle strength. And this is something that we hadn't thought about before, but now we're exploring, like, how does that work, and can we actually leverage that information in a different way, a more general approach to making muscle stronger. So the future directions for this, at the moment I'm studying this whole process in human cells, so getting cells from biopsies or myoblasts that are in culture, that are grown in the dish, and seeing how do those cells behave, do we see the same thing, and then the idea is to take this information towards DUX4. So we have, as previous speakers explained, we have several models, several ways to study that now in mice and as well in cells in the dish, and asking, well, what happens if we add U1 snRNA to DUX4? Do we start seeing something? Do the cells survive better? Are they happier? And that way we can get to the real point, right? Getting to testing possible treatments in cells that have DUX4. And this is still a long way out to actually getting to the clinical trials. But ultimately, it's a feasible route worth testing. That brings me to acknowledgement slide. I've been doing this work in the lab of Dr. Tom Rando, the guy dressed in white on the left here. I am in the back. Tall guys are always in the back in these photos. And this was made possible initially by funding from the FSH Society, later on by MDA, and currently by the NIH. And with that, I thank you for your attention.
Stephen and Jeff want to come back up. We have time for some questions. Does anybody have any questions right off the top? Yeah.
I was wondering if the slide, I'm wondering whether the slides could be shared with the audience. I don't know, because it is a good summary and, oh, I'm sorry.
No, you're good.
Should I repeat?
Can we share the slides because?
Yes, because for many people it may be like an abstract, a reminder of all the information that's been given out.
So June, I've got another one.
Okay. Well, I will discuss that with the speakers. They're usually very generous about sharing slides. They might have to remove something that's like unpublished data, but we would love to
add a few advertisements in there, but
yes. So we will.
Send money will be added. But
Yeah. Yes, we will. We would love to share them. So keep an eye out for that.
Any other questions?
I guess this is mainly for Dr. Statland. You referenced the Duchenne muscular dystrophy process to getting approval and using primarily biomarkers, I think you said. I'm wondering if you could talk a little bit more about what was needed and what's happened since the drug was approved, almost like phase 4. Do we know much about that at this point?
Yeah, so actually in my talk I was referring to using manual muscle testing to get a drug approved, which was in Plaza. It's really a fascinating story because the study that was done to get that approval was done 21 years ago, and the researchers, for whatever reason, never really published it. And so it finally got published about 2 to 3 years ago, and a drug company was able to take that data, and the FDA agreed to accept strength as an outcome measure to show improvement for muscular dystrophy. So in that sense, slightly different than a biomarker because they had shown improvements in strength. But you're right, there was a drug approved for Duchenne muscular dystrophy based purely on a biomarker, which was a change in dystrophin that was very small. This was a gene directed therapy for Duchenne muscular dystrophy. Some of you may have read about it because it was a scandal in the news when it happened. It's called Exondys, and it increased the amount of dystrophin in a muscle biopsy by less than 1%. And the FDA took the position that this was the fundamental problem in Duchenne muscular dystrophy, and so if it was corrected over time, you could reasonably assume there would be a functional benefit. There really was no post-marketing study. And so this is a separate topic, and Dr. Day can talk to you about it. It's sort of more of a social conversation, what happens when drugs are approved using accelerated pathways where they approve them based on biomarkers. The accelerated pathway is the FDA's process for us to try to get drugs faster to groups of people who have rare diseases where there are really no treatments. And so I think it's a good thing to have it, but it does set up a scenario where a drug might get approved before you have that definitive benefit shown. For that particular drug, we're learning more as it's rolling out. Of course, that is getting eclipsed in the field of Duchenne muscular dystrophy by gene therapies that are now coming out where the size of the effect is just astronomically larger. I hope that helped.
Yeah, well, I kind of use that as a mental model for what we're, project us 5, 10 years out.
Yeah, what we're hoping to do is to learn from that experience. And so I think, Dr. Tapscott's been starting really to help us move forward with this, that we can understand our biomarkers we're using and try to gain the data now to help support that tie between the biomarker and the functional benefit. So when we have that drug, it's going for approval, we can be more confident that if that biomarker shifts, that, yeah, we should keep taking that medication, whatever it would be.
I have a question about DUX4, in that I understand it's really harmful in some muscle cells, probably most. But have we proven, and by we I mean you guys, proven that it's not useful in other cells of the body, in other processes?
It is useful. It's, as I tried to emphasize, it's expressed at the 4-cell stage embryo where it's necessary to drive that. Whether it's, and it's also expressed in the male testes, probably in the spermatogonia. Whether it's necessary in any other adult tissues is unknown. We've looked, other people have looked. There's some suggestions that some tissues might have low levels of DUX4, but at this point, we don't know of any other tissue that requires DUX4 in the adult.
So systemic treatment could be kind of tricky or dangerous to...
Well, right now, it would be cautionary for women who want to have a pregnancy, yeah. And it might be a male birth control.
Yeah. That's and then in follow-up for Dr. Morree, could this, those sequences, I'm thinking FSH seems to manifest itself in some muscle cells more than others and across the board. Could that sequencing be the, what makes some muscles more susceptible to it?
Yeah, that's one of the more intriguing questions on muscle in general. You have so many muscles, and you'd imagine they're all the same, but they're clearly not. And with each muscle disease, there seems to be a different pattern of muscles being affected. And the molecular basis of that's up for grabs. We really have no idea. So in that sense, it's certainly very exciting that we're finding this pattern difference between those different populations. And that's something similar, certainly, that I personally want to dissect further and ask, could that underlie some of the differences that we're seeing? But that's very speculative at this moment. Yeah. Absolutely, absolutely.
Okay, this was for Steve. I noticed you had a study with albuterol, which is a beta agonist, and I was wondering, given the sort of universality of beta blockers in the population, and there's also been some reports of it's producing rather significant weakness in people, whether that's ever been looked at. It's sort of the inverse of the albuterol study.
I think it's a fascinating question, and maybe I could turn this over to Jeff, who might have more knowledge about the clinical work in that regard, but I'll get on it for homework tonight.
Yeah, no, that's one of those excellent questions that you think would come up and we would have already looked at it. No, we haven't looked at it. It's difficult to look at because it's a very ubiquitous medicine, and so you would need a large population to look at that in. But I think that that's something we could probably start to think about looking at using some of the resources we have, like the registry that does have several hundreds of individuals in it, where there are ways to follow what happened to them over time. And that'll be on my list of things to look at. Yeah.
But also, I mean, we can just go to the lab this weekend and put beta blockers on the tissue culture cells and see if it has the opposite effect. And if you give me your email address, I'll let you know.
This is where somebody like me would kick into gear and
Another question I had is because usually muscles are stimulated by nerves because they're all innervated. So here we've talked about pharmacology, therapeutic drugs at the topical level, let's say muscle cells. To what extent are proper or improper neurostimulation of a particular muscle make it worse, or could it make it better?
Basically, it does, it's kind of a, does exercise make it better?
Yeah, I want to make sure I understood the question. Are you asking, would exercise make something better or worse, or actually electrically stimulating the nerve? Oh, so you mean like because you can buy electrical stimulators for the nerve, for the muscle?
Well, so I'm not thinking so much as the therapeutic aspect of electrical stimulation, so to speak, but whether, at first I was thinking of FSH as maybe being fully innovative for whatever reason it
Oh.
to be, thereby generating the muscular dystrophy or atrophy of the muscle. Is that really a serious reason for FSH?
Right. I mean, I think the primary problem in FSHD is in the muscle as opposed to, in the nerve. So in that sense, I think the work that's going on makes the most sense to me. Yeah.
Right, so so basically you are approaching the question as basically the muscle being denervated, so to speak, and then you're focusing on therapeutic.
So I think we're approaching it thinking the muscles are still innervated, but the muscles themselves are starting to die. Now, once they start to die, that innervation will be affected. Yeah. And but coming from the muscle side, not the nerve side.
I was wondering why Stanford isn't one of the clinical study sites, considering how much research is going on at Stanford here. That's one first question.
All right, so we are looking to expand. We don't have the names of those sites out yet, but Stanford is certainly, very high on our list. We would love to have Stanford in the network, and so that we're aware of that, and that we're hoping that would be something in the near future.
Okay.
Yeah.
Yeah, we're hoping as well.
Yeah.
Second question is regarding ACE-083, which apparently is showing promising results. Do we anticipate any time in the short future to have it available either here or anywhere in the world for commercial use?
Right. So
Maybe not approved necessarily by FDA, but
yeah, so so let's just say where are they at? So it is an investigational drug. They're directly injecting it into muscles. What they've done so far is what's called a phase 1 study. They've done an open label study where they injected muscles and then increased the dose. What they've been able to show is that the muscles will get bigger if you inject them, about 15% bigger. What they haven't shown is that there's any functional benefit from that occurring. The current study that's going on right now has a placebo arm, so we can start to get at this question of whether there's actually a functional benefit from that change in the muscle size. Let's say that they show it's positive and people are improving with the treatment. From the pathway for drug development in a drug like this, they would likely have to do another larger study first before it would be able to be considered for approval. So you're still probably looking at several years.
Thank you.
Yeah.
Hi, thanks for the talks. They're all really interesting. I actually work in the tech industry, surprise, surprise. So I found a lot of what you guys talked about somewhat paralleling the work I do. And the last speaker, you mentioned that you were looking at, trying to look at genes that are like 100 nanometers or less. And in the tech industry, we have tech, I work in the silicon industry, so we look at transistors that are much smaller than 100 nanometers. And I wonder if you ever talked to any of the tech companies in the area to see if you can like borrow some of their microscopes to see if you can see the smaller sizes with them.
Yeah, it's definitely an area of development, building new microscopes to doing this. The challenge that I didn't mention is not simply that it's 200 nanometers in length, but it's one letter in depth.
Okay.
And that's really the issue. So at the moment, we've solved it, and we're definitely talking to the people who are more on the physical side, developing these kind of assays and developing these kind of technologies to make that imaging more important. So in that sense, it's really great indeed that we are here in the area where people are on that technology side. So thank you for raising that.
Yep, thanks.
I could talk to you guys all day. For Dr. Statland, with your graph about muscle strength over time, I think it was the responsiveness chart you were talking about, you had change over SD, the standard deviation, I'm guessing. For each of those points, the X was the mean or the average?
Yeah, exactly.
And so if you took individual people and ran them, would there be any patterns?
That 3% number I gave you per year actually came from a subgroup of people that we had more extended measurements from.
Okay.
Yeah, and so you can see that slope in the 12-month change on the graph, but then we had a subgroup who we could follow for 7 to 8 years, and it just showed that was a consistent change for them.
Okay, good. That's like taking those last ones
Yeah.
out. Thank you.
Gentlemen, thank you very much. It's very informative. I'm curious to ask you what your thoughts are on CRISPR. Sorry, I got a big mouth.
It's a very powerful technology, and it's certainly driven research. There are many people using CRISPR combined with viral delivery systems in different human diseases. I think the most advanced studies are in Duchenne muscular dystrophy.
Can I just ask right there, why, I always hear about Duchenne. Why does that seem to be more? Why, is it a money issue? Like, what is it that Duchenne seems to get a lot of attention?
Theoretically, it's an easier disease. It's a standard mutation. It's, you're disrupting the function of a gene, and so replacing the function of that gene by correcting a mutation or a splice site. As I tried to explain, FSHD is complicated. We understand it, but it is complicated. And so the therapeutics there on a genetic basis are not necessarily as straightforward. However, having said that, there are approaches that parallel the CRISPR approaches in Duchenne. The reason I mentioned Duchenne is that's one that's probably going to get to clinical trials before FSHD. But there, if you can show delivery to the muscle in Duchenne, then there are approaches in FSHD that could be used. So I think it's just going to lag behind by just a little bit, but it's a very important technology.
Are you working in that area at all, or in the CRISPR area?
Well, we and others are using CRISPR on a research basis, and there are published studies using CRISPR either to delete the array entirely so you don't have DUX4, or really very effectively to target a repressor. So in the CRISPR technology, you use an RNA guide to target an enzyme that cuts the DNA. You can use that same technology using an RNA guide to something that represses gene expression. And it's been shown, I think, by Peter Jones that you can, silence DUX4 using that technology. So then it becomes a delivery issue. And that's why I'm saying that, you really have to get viral delivery or some mechanism of delivering this to all of the muscles in the body. And as Jeff mentioned, there is a current study in Duchenne asking, can you deliver to all the muscles in the body using a virus? If that works, then the gates are open to try this in FSHD.
But I've read that it seems like because it's a repeating thing as opposed to a cancer, when you go into CRISPR, that it seems like it's a little bit more helpful to people like us.
Well, there are hundreds and hundreds of copies of the D4Z4 in the genome, and if you were to cut them all with CRISPR, it could be a disaster, right? But targeting a silencer there makes sense.
Thank you.
Other questions? Great. Well, let's give our speakers a hand. And we'll take a short break now. We'll start again at 3:15. So there are beverages at the back of the hall and refreshments, actually snacks. So please, and the restrooms are just down the hall.